looking at the stretched screen and the thought, it almost looks normal now, right? Which means when you leave this room and go back into the real world, everything will look kind of in the wrong proportion. So I was listening to the previous speaker, and we have a lot in common in terms of technical work. Everything I'll be talking about today is real time, but not real time enough to run a spaceship, to control a spaceship, right? So it's not, milliseconds, but we do feature computation in real time. I'll talk about it in detail. In many ways, the previous talk gives you an introduction to what I'm going to say. I guess the only difference is that we can say who is using this stuff. I'm from Meta, so basically Facebook, Instagram, core services. There are hundreds of product teams that use this work. And the material here is from our KDD 2022 paper. This was in the applied data science track, the deployed category. And you can find the paper in the archive, a lot of details, including the deployment experience. Let me see. Okay, good. So again, look, I was looking at the previous presentation and I added a slide here just to tell you a bit about me. So you can ask about any of these experiences. I started as a graduate student in math at UCLA, then switched to computer science, finished the PhD, taught at the University of Michigan as a professor for many years. I taught algorithms, did research on algorithms, did research on chip design, quantum computing, still do some of it on the side. I was a visiting professor at Stanford, taught intro to VLSI, worked at Google for almost 4 years on search infrastructure. Also, a fairly real-time system that processes a huge amount of data. And at Facebook, now Meta, I worked on user integrity, on crisis response and misinformation. Then I moved to the probability organization, worked at AI platforms. The smart decisions group is where I am now, and this was really part of the probability and then part of AI platforms. So the last 2 bullets there are the same thing. Originally I'm from Kyiv, Ukraine. I've also been a director at Nova Ukraine, which is a nonprofit here in the Bay Area. We raised 64 million this year for projects in Ukraine. We run a lot of medical projects, evacuation, what have you. Now, in this talk, I'll discuss the context for this work. And I realize there are people of different degrees of technical background here. So I'll put a lot of emphasis on why we are doing what we are doing and what the terms mean. I'll discuss different types of platforms, and specifically the Looper platform. I even have a t-shirt with Looper on it. That's really what we are working on. I'll discuss example applications and some statistics, deployment experience, and then future work. And I can say that I just submitted yesterday for publication approval our next paper on the future of end-to-end systems. So there's a lot to say along these lines. Okay. The notion of smart strategies is very important. That's what we support in our platform. We don't do general intelligence, general artificial intelligence. It's a fairly well-defined context. And the idea is that you're developing some software. It's not necessarily a recommendation system that is entirely designed on top of AI or with AI from the very beginning. You have some application. Maybe it is AI sensitive, maybe not, but you want to optimize some decision points in this application. So when I say decision or prediction, it doesn't really refer to the decision about product strategy. It refers to decisions or outputs. We call them also AI outputs, of which you may have 5 million per second. And our system supports all these things, right? So you want, for example, to configure the video codec for uploading a video or for watching a video. You want to sort the notifications in the Facebook app, right? Or some of these things on Instagram. But the point is, these are fairly small things. There are many of them. You can't build an entirely new pipeline and maintain it just for this application because there are so many of them. They can be important. They can drive product metrics. They can drive some monetary optimizations and so on. In fact, the application that drives, that brings most financial results of all the ones that we have, not counting user engagement, it makes one inference in 30 seconds. But each inference is very important. But then, of course, there are much more voluminous applications. Okay, so you have products interacting with many users and or the environment. And by users, I really mean Facebook users, Instagram users, whatever. The environment can be, for example, some technological environment. You may have a server, some files get uploaded, downloaded. You may predict whether caching is useful for this file, right? And so closed form policies typically are far from optimal. Product engineers, they often start with some heuristics or policies, something starts working, then they realize you can do much better. But you need to learn from data. So that's really the key. Smart strategies are ML models and or policies that learn from data and they personalize the AI outputs, decisions, predictions, and so on. You may be predicting how long will it take to do something, right? Upload a file, right? Or how long will the user wait until the click? Okay, so many examples here, application settings and preferences online on the phone screen, you have very little space. Users don't even know where to configure all these things. So you want to set some defaults, right, intelligently. And sometimes you don't want to use the defaults. How do you decide? There's no rhyme or reason, you just learn from data. There are adaptive interfaces, again, with limited screen or limited VR headset, limited kind of vision in a limited vision space in the headset. You only want to show the options that are of interest to users, right? In the Facebook app, there are a lot of things probably you haven't even seen because it doesn't show them to you. Maybe some people are interested in dating, some people are not. Some people want to look at the marketplace, some don't. And how do you decide this? You use smart strategies, okay? So frequency of ads, user notification, prefetching, content ranking, notification, lots of interesting applications. Okay. Now, I'll have a few of these lists in the presentation. They all took a while to get right. And this list has 2 parts, 1 and 2. So I think 9 or 10 points here. Now, the data distributions that we work with are non-stationary. And they're also not matched by closed form loss functions, okay? I covered the first 2. So long-term product objectives need to be learned from data. And even when you optimize them, they use normalized entropy, they use some list ranking objectives. That's a good first shot for many applications, but at the end, it's not closed form and you have to learn all these things. And data drifts are very important for online applications. People watch the TV, they want to do one thing, then next week something happens in the world and people have different interests. So again, you need to learn this from data and you have to relearn very often. Now, compare this to large language models that you build over months. Language doesn't change that much. This is a different problem. You have to train quickly, you have to adjust quickly, and then of course you have to do real-time inference with real-time feature engineering. Now, when you build models to predict something, you capture some correlations in data. That's kind of what you do, right? There is no fundamental understanding of in these models. And even if there were, the only way to make sure that your product impact is significant and positive is to try a causal experiment, such as A/B testing. There are many network effects, there are many indirect things that you can't model well. You can build a great model, optimize the function all the way, and then you try it in the product and everything works backwards because maybe there is some kind of unexpected reaction, right, in the world to what you deployed. So you have to try this and you have to do this often. You have to do this for every new model you build to address the data drift, okay? Now, when we submitted this paper to KDD and the reviews came back, one of the reviewers said, I understand your paper, great paper, but I don't understand, where do you get clean data to evaluate models? And the answer is, there is no clean data. You get the data, and I'll explain how we do data ingestion. There is no correct answer to many of these things, right? You don't know, for sure that this file should definitely be prefetched. You can learn later whether it was needed, right? And so At the end, you just evaluate everything by A/B testing. You have a product, you run the product without the machine learning, decisions, and then you have another set of users and you compare the results and you compare the product metrics. This is how you go beyond loss functions. Okay. Another point, once you do A/B testing, it treats all the users the same. And by users, I mean end users. So it turns out you have to personalize A/B testing. Even if you want to know whether a light blue button is better than a dark blue button, turns out some people like light blue, some people like dark blue. Okay. So one of the applications in our system, and now in this newer, what we call it actually a separate platform, we can build a model that automatically predicts which people will like the blue button, which people will like the dark blue button, and then we can test this new model with personalized testing. And then you can also do this to other ML. So if you have some ML treatment like caching, prefetching, whatever, you can test that with personalization. Okay. Number 6, this should be obvious, right? Platforms to train, host, and monitor large numbers of ML models are needed, and they promise economies of scale. So our model, our platform is designed for internal use at Meta, but we have hundreds of use cases, right? And there is significant demand, and we don't want people to build the same thing over and over, even if they can. Okay. Real-time feature extraction and inference are required in many cases. And unfortunately, they're a lot less efficient than a synchronous batch mode process. And if you look at some end-to-end systems published like Uber Michelangelo, they're batch processing, at least the way they were described in the literature. But for us, if someone clicks on some page and this goes into a database, then we will need to account for this click as quickly as possible. Maybe not in 400 milliseconds, but we will go and get the data, and we'll have to compute some kind of count in a table, right, to get the count right, to accommodate this recent update. Okay. And so then number 8, product engineers often don't have ML background, and we want them to be productive in designing products. So the way this works, you write your software, and until recently it was mostly in PHP for this platform, meaning the products were in PHP. Then you had some API that interacts with our platform, it's RPC API, and then you get the AI outputs. Okay. So these product engineers, it's not that they don't need to write any code, they need to write code using API, but they don't need to write any ML code. And if you want to write ML code, there are also ways to do this. Okay. Now, this is straight from the paper, and there's no way I can explain it all. I'll give you kind of main ideas behind this picture. So this picture compares several concepts. It compares, well, first of all, before we even get there, there's what we call frameworks, ML frameworks, such as PyTorch, TensorFlow. There are toolboxes. They give you tools, you can use them any way you like. They don't give you services, okay? Then you have horizontal ML platforms that give you services, storage, pipelines, joins, inference. And then you have vertical platforms, and these are the 2 columns for vertical platforms that cover the entire ML development cycle and use cycle. And in the literature, there are many platforms that, not many, but some, claiming to be end-to-end. Our end-to-end is wider. And so our end-to-end starts with a selection of problem type, which can be automated. Our system can now decide whether to use supervised learning or reinforcement learning. And then data sources and collection. And then at the end, we have product impact evaluation and optimization. We can tune the hyperparameters of a model to optimize user engagement, which is much better than optimizing some loss function. Okay. Now, the 2 columns compare specialized vertical platforms that are designed often around AI-driven applications like speech processing or image understanding. And there are also general purpose vertical platforms. What we do, the Looper platform is general purpose, but the PEX application I'll explain is really a special purpose vertical platform. So we have kind of 2 things on the same infrastructure. Okay, and this flow goes top down, but you often have to come back and redo things to improve results. That's in particular optimization for product input. Okay, if there are some really quick questions, I can take if the yes or no question, or if there's a numerical answer, I can take that. You can interrupt me, but for longer things, maybe we'll wait until the end. Okay, to give you more context about what we do, the philosophy here is that we are designing a platform to support workflows. That's really what platforms do. And it's not a toolbox, it's not a framework, it's not a horizontal platform. We use horizontal platforms. There are quite a few such services available at Meta, as you can imagine. But these workflows are typically what's not automated. These are repetitive maintenance operations, laborious, code writing, such as setting up pipelines, making sure everything works, testing. People like doing this once, twice, but then it gets very boring. And it's also slow and error prone and so on. So basically, there are some also operations that are difficult to reason about. And I mentioned tuning to product metrics. It's taking a long time. It's a little bit like, I don't know if you know someone who does like biology students or medicine students, they go into the lab and something is there growing in the little petri dish, and it takes time, and then you come back next day and it's all dead. You cannot really do it quickly, and it's easy to make mistakes. So developing these long pipelines and complicated systems is kind of like that. It's grueling. So you want to automate this, and you want to make sure it's working correctly. Now, our platform design philosophy includes several concepts. Application context is essentially the features and how you get the features for decisions. Okay, that's a simple way of explaining it. For example, many of our predictions are about end users or maybe Facebook pages. So you have the context of a user and everything we know about the user that we can get in real time. Okay, how many times the user clicked on something? What is the account age? What is the zip code? Whatever. Okay, if it's a page, there are other features. So this is the context. Then there are product metrics, such as daily active people, right? How many people, use Facebook or something specific on Facebook? They're often noisy, delayed in time, and the cause and effect relation is kind of muddled. Okay, so to set up ML, we need a proxy ML task, right? We want to predict something, and the way we do this, we focus on applications where the correct decision, or at least some information about the correct decision, are known soon after the decision needs to be made. Let me repeat this. Our platform makes a prediction or a decision, and then soon after, you can collect some data that tells you whether this was a good output, a good decision or not. For example, you decide whether to cache a file, and then 5 minutes later, check if this file was needed. If it wasn't needed, then it shouldn't have been cached. Okay, and vice versa. It's a noisy feedback, but it's useful. Okay, and so of course, all these effects are evaluated on live data, right? Very different from just causal, right? Where we optimize the loss function. So in this work, and this is a simplified statement of contributions, we have a vertical end-to-end platform called Looper, and more general design principles that you could use for other platforms. Right, vertical here means it goes all the way from data collection and product and problem type selection to product metric evaluation and optimization. And basically, we extend the notion of end-to-end because typical end-to-end systems don't go that far. Okay, so I'll tell you more about data collection and about A/B testing, but we have specific improvements, and HTE is the heterogeneous treatment effects. That's what I told you about with blue buttons, light blue and dark blue, where some people like one color, some people like a different color. Again, in medicine, if someone evaluates a new medication, like say for hypertension, some people will benefit from it and some people will have life-threatening conditions. So you have to really use some features, right, to decide who can use what. Now, this is more of a background. So machine learning to support smart strategies. As I already mentioned, we need to approximate product goals with predictable outcomes, right? And we use not only ML models, but also decision policies. A simple example, if you're doing binary classification, you build a classifier, it produces a score between 0 and 1. You decide where to cut score. If the threshold is, say, 0.5, then whatever is above gives you yes, whatever is below gives you no, okay? And you have to choose appropriate machine learning models. So on the right, you see two histograms, and the smaller one, let me see, shows model type. So GBDTs, decision trees, or XGBoost, if you will, are used much more often than sparse enance, than reinforcement learning. And PyTorch Mobile, we actually moved from our platform. We don't have it anymore. It's separate. So this is interesting. And GBDTs, that's a simpler model, kind of more older generation. But in practice, it often beats deep learning. It can use less data. Inference is much faster. Memory size is like 10 times smaller. So that's something to keep in mind. Our platform can choose the model type for you. Okay. For the task, you have let's go bottom up. You have binary classification, and it looks huge. It looks like almost everything is binary classification. It's a little misleading because ranking we do using binary classification. Let me explain this. So you have 5 things to rank, right? The binary classifier predicts whether something should be on top. So it gives a score, right? Something, let's say item number 3 gets score 0.9, item number 4 gets score 0.7. You sort by these scores, you get a rank. The things on top are more likely to be correct. Okay, so then there is regression, which gives you a value. It predicts latency or something like this. Then there is contextual bandit, where the feedback is very noisy, probabilistic. MC is multi, so we have MT multitask, and MC is multi-class classification, so not binary. And RL is reinforcement learning. It's now grown in acceptance. It's kind of difficult to set up, but it has significant benefits in some cases. Okay. Okay. So this is an important concept in understanding how we streamline data collection. Typically, ML is data-centric. And if you listen to Andrew Ng, he will tell you about saving data, cleaning data, how important that is. All true. However, in applications that we are handling, often this is unnecessary, and it makes it much more difficult to automate the entire cycle and to ensure reproducibility. If you clean your data by hands, there goes your reproducibility. You can't repeat anything. You have to retrain every day, as we often do. Who's going to clean the data? So for us, data collection is software-centric. It's done using APIs. And by the way, our entire Looper API, at least the simpler version, has 2 calls. And I'll talk about this a couple of slides later. Basically, these 2 calls accomplish 3 things. First, they collect the inputs, okay, where you want to make a prediction or decision. Then they make the prediction or decision. This is 1 call. And then 5 minutes later, you observe something that will help you improve your model. Okay. If you got the inputs and you don't have a model yet, it returns null. Okay. So very simple. And this is all we do for data collection. So it turns out that the platform has a complete custody of data. The customer, the client of the platform, which is not the same as end user, they don't need to maintain training tables. Everything is done, everything is reproducible every day if there's an update. Done automatically, right, with monitor. And so there's data abstraction. That's convenient. If there is some kind of software update or whatever update, the customer doesn't care. The platform takes care of this, which makes it a little difficult to maintain the platform, but it's much more efficient this way. Okay, and so you can reason about training. Do you want to train every day? Do you want to wait for enough data? Many different policies possible. And another aspect of this is an online-first approach. We log features and labels. Labels are these feedbacks 5 minutes later. We log them separately, then join in real time. Okay, this prevents so many possible problems. You could have data leakage where the labels, where the inputs have some of the label information. Discrepancies. They're just, if you look at the papers that solve all these problems, it's not worth it. Just do it this way. It's simpler, right? Online first. And another point that this ensures is that when you train and when you do online inference, all the feature processing is exactly the same. It's not only matching, it's literally the same everything. Okay. Now, this is a slide I took from a slightly different presentation, but it shows the user journey on Looper. And I guess the most interesting part here is the arrows and the weeks. It just tells you how quickly one can set up a product engineer with no knowledge of ML can set up a use case on Looper. right? So they first create a use case. We have a user interface, and they basically need to add some features. Then the second thing, write code. This is not ML code. This is product code. They're product engineers. They should be able to write some product code to get the features. Now, there refers to essentially code in PHP at Facebook, at Meta, that runs the applications on the web. It's the web tier. Now we added interfaces for other languages. We can now do everything. Python, C++, basically much more general interface, just a matter of an API. Okay. And so you create a couple of classes, and that takes a couple of days. You read the wikis and all that. Then you automatically run daily with new data. And at first, there's no prediction because there is no model. You just collect the data. You collect the observations, you join them, and then you train the model. Okay, and you could do this every day if there's enough data. Then you tune decision policy. For binary classification, what is the cost of false positives? What is the cost of false negatives? Where do you move your threshold? Okay, and then you launch. And so altogether it takes under a month usually. Monitoring is very important. Again, if you're doing causal, you optimize the model, submit it, you won the contest, you're happy. For us, you have to make sure this thing works every day, doesn't drift, and if something happens, you at least need to be aware of it. Okay? Any questions here? Anything I can quickly answer? No? Okay. I'm super clear or super confusing? One of those. Okay, this is a long slide. I will not get into too much detail. There's I think half a page in the paper discussing this step by step. But step number one, use the client API to get the features, try to make a prediction, and then possibly later observe the correct output or the hint. The blueprint here, I'll discuss it in more detail in 2 slides. It's basically a configuration of everything. Okay, not just the model. And the reason it's part of the experimentation system is that before you launch, you have to try a couple of configurations. They all have different configurations. You have to maintain them. You have to be able to restore them. So it's a separate, fairly detailed component. Then number 3, you extract features. The configuration includes data on which features you're going to extract, which versions of features, and so on. Then you try to make a prediction. If you have a model, the predictor gives you a prediction. If not, it gives you a null. That's okay. You collect the data. Then you log data, you log the observations, you join them in real time. Then you, in number 6, you perform training, right? Or you prepare tables, then you perform training, and you got a model. So when you have this model, you publish it into the predictor. It's not yet used in the product. You don't know if it's any good. Maybe it was, something glitched to there. So what you do in number 9, you publish a canary. A canary is a shadow model that makes decisions on real data, but doesn't affect the product. Okay, and we're now working on a canary that allows to check product impact directly. Here, in the system described in this paper, you're only checking the loss function, which is a good sanity check. And if the loss function improves, or at least is acceptable, if it's not a catastrophic failure, then you promote the canary into the production. This is done in the blueprint. You have update the version of the model that you're querying. And so the config system takes care of this and the cycle repeats. Okay. Good. Moving on. So the strategy blueprint that I just mentioned, it's basically a quadruple configuration. It ensures that the configuration is separate from code, right? That's very important for code stability and for configuration stability. And if the configuration is part of the code, it's very hard to do experiments. You can't try 5 different things. So feature configuration, label configuration, model configuration, policy configuration. We now actually have a 5th one for product metrics. We now added product metrics into this blueprint. So there's full versioning. These configurations are immutable, meaning you can't modify any number. You just create a new version, copy, and then something changes there. So you have the complete history. You cannot lose anything. It supports these vertical optimizations where you modify the decision policy and the model hyperparameters at the same time to get greater benefits. Okay, this is how it looks. This really is an expanded version of the first few items in the earlier diagram. So you have in the adaptive experimentation system, and adaptive means that you try an experiment based on the results, you try a different experiment, change some parameters or whatever. That starts with target product metrics. You are trying to optimize user engagement, or maybe file throughput, or maybe bandwidth to the cell phone for caching and prefetching. And so this is done using A/B tests, but you try a whole bunch of A/B tests, and then you use these A/B tests to optimize, say, hyperparameters or decision policies or both. And we do this using Bayesian optimization. So it's very efficient in terms of how many experiments you need to run, because all of these experiments are on real end users. And if you run too many, you undermine user experience. So the experimentation system creates a blueprint version and maintains multiple versions. Then the API reads those versions every time you try to make a prediction or log data. And then this is really how it looks. So version 1, version 2, it's not like, Python version 1, version 2. You can have 20 versions for a particular product. You just basically, every time you modify something, you create a new version. Okay, and so you have these 4, now we have 5. And then the training table, which has the features, the labels, the version of the blueprint, and then the training system has full information explicitly, not explicitly recorded in one place. And then your model is reproducible because you have all these configurations in one place. Okay, great. I think it's going to get easier now. If this was too detailed or too boring. So specializations. I described the core system, but there are specializations to ranking, where we, for example, support, there's concepts related to ranking. You could improve ranking objectives. There's something called positional bias. People are more likely to click on the first item, even if it's equally good as the second item, and just more detailed API. So this is something we haven't fully done, but it's kind of on the way. Integrated experiment optimizations, A/B testing. This is much more significant. This is practically a second platform that we are maintaining. Okay, and I'll describe it's called PEX, personalized experimentation. So I talked about HTEs, heterogeneous treatment effects, and we have automatic personalization because we have a lot of data about users. And in order to predict whether you use light blue, whether you prefer light blue or dark blue button, you can use everything that's available legally about you on our platform. And as I mentioned, optimization of product impact is done using Bayesian optimization to minimize the number of attempts. Okay, great. Couple of other examples. Data prefetching, I alluded to it several times. Basically, these are typical applications within meta systems, right? There are different parts of meta that use data, store data, prefetch data. You just try to predict whether something is going to be needed again within the next 5 or 10 minutes. Okay, and one specific, I guess not specific, but a more specific category, there's something called GraphQL, which is a language for data and for querying data. And so basically in GraphQL, in these applications at Meta, we were able to save 2% compute resources at peak server load by optimizing data prefetching. If you don't know what GraphQL is, just skip this, not a big deal for this presentation, but a big deal in practice. Now, a second example is predictive screen rendering by Meta's app client for low-end devices. If you have an old phone that takes a long time to download something and to render, then in order to get snappier user experience, you want to download something or prefetch some pictures or whatever else. But if you do this too often, then you overload the bandwidth. So again, it's a binary classification to prefetch, to download or not. And the insight here, somewhat surprising, is that instead of just taking all the features that we have about you, right? What we do, we pack some of these features into user embeddings. So for every user, there's a vector in some latent space, 128 dimensional, I think. And it basically is a feature. It's a tensor feature that we use. And these things are updated in real time. In practice, kind of a lot of pain to maintain this at the platform level. Okay, application example. So personalized experimentation. Here, there is kind of a light bulb moment, at least it was for us. So connecting A/B testing, which gives you feedback, right? When you test something, you get, a user did better with this treatment or not, right? The user liked something or not. So with A/B testing, you get labels. That's the light bulb moment. And we use these labels to train models, even if the application didn't call for any ML model. We try to predict which users benefit from what, okay? So there's ML out of almost nothing here. and the interface matches perfectly well. So we basically have this experiment optimization system based on heterogeneous treatment effects, simple learning curve. People used to do this by hand and still do at Meta, but it just streamlines the entire process. You could do more experiments, more impact, better optimization, and all that. Another thing is, in practice, when you work with product impact, it's not one metric. It's a whole bunch of metrics that you care about. In some cases, if you mistype your password on Facebook, you can get an SMS message, or you get an email, or you get another attempt. Which of this to use depends on a couple of circumstances, okay? And so basically, the objectives here are the cost of SMS that Meta needs to pay for, or the email, or how many users actually get through the login prompt with this, right? It turns out balancing multiple objectives is not something people naturally do, at least not with a lot of numbers, and we can automate that too. Okay, the impact and adoption of Looper. Looper is used by 70 plus, it's a little, I think it's 90 plus now at Meta. And there are 400 to 1,000 models running at the same time. When we just announced Looper, within a few months, there was a surge of adoption and people tried a lot of stuff. And many of these models were, kind of models to be evaluated. And if you have 5 models, you take the one that's better. So we can run, 1,000 models, but in practice, when these models are already optimized, you don't need to run as many. So we basically make 4 to 6 million predictions per second in all of these, different, I think there are like 270 use cases as of last week, fluctuate, sometimes more, sometimes less. Sometimes teams use this platform to quickly create a use case and then move it to a specialized infrastructure 2 months later. Good enough, useful still. These are categories that we kind of use to summarize the applications. There's personalized experience, as we discussed. There is ranking, prefetching, user notifications, prompts, and value estimation, predicting latency or memory usage of a data query or something else. Okay, and so typical adoption at Facebook and at Instagram doesn't require additional staffing in product teams. So people who don't know ML use the system and get running in a month or 2 months. We have some power users. We have some users who require additional infrastructure, additional interfaces. So there are different tiers of customers, self-serve customers, customers who need white glove support, or strategic customers. It's common for Looper to contribute 20 to 40% of improvements per quarter or per half in particular goal metrics. Every product team has a goal. In this half, we improve something, user engagement by so many %. So Looper is very helpful in this case. And one trouble we have is there are different product metrics. It's hard to aggregate them. Okay, adoption curve. I kind of mentioned this, but I configure the configuration takes up to 2 days, usually much faster. Training the model on product feedback and revising it 1 to 2 weeks. Online product experiment 2 to 4 weeks. The numbers here are a little different from the slide I showed you. That slide is more recent. This was the result of a survey. And the slide was the result of basically averaging data we measured. And so product launch, product launch 1 to 2 months after the initial data collection. And this is done without technical depth. Everything works. I had an intern from January to May. He improved some models. He went to product teams asking, would you like a better model for your product? And they stared at him, 4 different teams out of like 10, and said, which model? He says, well, we're from Looper. We maintain some applications for you. I said, we don't know about Looper. Turns out there were teams that ran applications on Looper for 2 years. Some people leave, some people come back. They forgot. It just works. And it retrains every night, right? So that's low technical debt. It's not some hero developer who built a prototype in 3 weeks, and then people have to maintain it because it breaks all the time. No, it just works. And so we have support for recurrent training, canary, model publishing, data visualization, and alerts if something goes wrong. But often nothing goes wrong. Sometimes there are data delays. We accommodate them. Half an hour later, everything is fine. So I'm running a little late, right? But I'll just a few more slides. Great. Impact on resource utilization. So this is more along the lines of deployment experience. And there's some interesting insights here, especially for real-time systems, real-time platforms. So this is kind of profiling data. You have 6 categories of applications, okay? And then for each category, we have 5 colors, which are different kind of ways time is spent. And we plot CPU resources. This is number of servers used per day, okay? And as you can imagine, the types of servers change at Meta, so this is just some units. Okay, look at the tallest bars. The tallest bar, this light blue or whatever color, turquoise, whatever it is, feature extraction. It's not model training. It's not model inference. That's very surprising. Why? Even though we train every night or every 2 days when there is less data, model training is not a problem in terms of resources because many of our models are GPTs. They're very optimized. They don't take a lot of time to train. You don't need GPUs. So for many of these applications, you don't need deep learning, turns out. You need deep learning if you have a lot of sparse features. Okay. Now, why is model inference fast? Again, GPTs, the inference in the paper, we have inference numbers, but the median is like, I think, single milliseconds, right? So I could say, yeah, if you want the response in 400 milliseconds, inference is just single milliseconds. But wait a minute, there is feature extraction. And so feature extraction in this case includes feature engineering real time. For example, adding up all those events to create counters. Counters are very useful features. If you're trying to predict something, you want to know how many times it happened in the past. Okay, and you have this as a real-time feature. So that takes a lot longer. And so the tail of inference plus feature extraction, the P99 is 240 to 250 milliseconds, which is much more significant than 7 milliseconds. Okay, now still, feature extraction is the bottleneck, often because of these engineered features. And it turns out you want to optimize it. So if you want to optimize this, choosing a better model, training, doesn't matter. You have, the bottleneck in feature extraction. So what do? You use fewer features. Now you can use 100 or 200 features, sometimes more, and many of them contribute very little. So it turns out feature selection is a big deal because it addresses the bottleneck. Okay, a topic for another talk, of course. Now, we looked into what makes this platform successful, and we looked in the literature first, what's known about the success and failure of these platforms. And we found a paper on why machine learning strategies fail, and it explains why people fail, which is good to know, but we want to know why people succeed in our platform. So we made a survey. It turns out that Looper helps address cases when you're manual optimizing parameters in large search spaces. It gets boring. I've done this before a number of times. When you want to figure out the correct values to make heuristics effective, turns out people developed heuristics for like every country, and then it just got boring to maintain, and then they started consolidating heuristics by countries and so on. No, just build a model. It will take care of it, and it will update itself, every day if needed. Creating of multiple objectives, and of course, as I said, updating the heuristic logic quickly, either because something changed or because the data has changed, right? Maybe your product changed, maybe the data, maybe something else. And so only 15% of the teams using our platforms include ML engineers, okay? Now, we had a lot of discussions recently how we can help more advanced users and kind of high-value models. So this is not in the slides, but I can tell you in short. The idea is to open up the architecture that I described, and this open architecture allows you using not entire end-to-end workflows, but partial workflows. For example, just training. Some people want to train their model, get their weights, and then use their serving architecture because it's so customized for their application. Perfectly fine. We basically are working on opening up the architecture, not outside the company, but opening it up in terms of product teams within Meta, so they can use partial workflows. In conclusion, smart strategies that I described enrich modern software and they learn from data. Okay, they can do things that cannot be captured by closed form expressions, and by learning from data, they can update themselves very quickly. Someone asked me before at previous talks, can you update more frequently than once per day? Of course we can. And 4 hours would not be a problem. Updating every 20 minutes may be a problem, but it depends on how much data you have. If you don't have a lot of data, of course we can. There's also incremental training, which we haven't explored. Everything is trained from scratch right now. So there are many efficiencies if we need them, that we could use. The smart strategies are supported by a vertical ML platform that doesn't require ML coding. You only need API coding in your product as a product designer or developer, and it's evaluated by product impact, not just the loss functions. Okay, so technically we extend the notion of end-to-end, and we have online first approach to data collection, RPC APIs. We have AutoML. This is an area of growth. We're putting more AutoML to basically automate check what people do and automate everything they do that can be automated. And so product impact is optimized via adaptive A/B testing and accounts for personalization and heterogeneous treatment. This is used in Facebook, Instagram products. Some internal systems can easily be used in VR, and there are a few others. Okay, that's it. Thank you for listening.
Take a few more questions.
Oh, absolutely, yeah. Question.
Let me give you a real-time scenario.
Yeah.
So right now, I have made this sales convention center. I opened my Facebook app. I checked into this convention center. So since you know, if Facebook knows that I checked into it, do you think that will give you an information based on the time and whether, okay, yeah, here are your nearby coffee location, or based on the right now, if you have based on the time.
So I'm very tempted to answer this question in one word, but I have to give a disclaimer first. So first, I can't tell you about how Facebook products work specifically, but technically, this is not a problem. This can be done easily. So if a product designer, if a product developer wants to make predictions based on your being here now, checking in, 20 minutes ago, that's not a problem with the system. The feature is available.
Real-time predictions can also be done.
Yes, they're real time in the sense that the features are updated, and in the sense that they're not batched. When we need to make a prediction, we don't wait for 20 more requests to batch them for efficiency, right? Two different parts of real time. Yeah.
Thank you.
Okay. Any other questions? Yes.
How important is the Bayesian optimization portion? And then also as a follow-up, like yes or no system, or what kind of pattern do you use? And then also if there are a lot of interesting Bayesian optimization.
Yeah. So yes, let me give you kind of a detailed answer with a couple of parts. First of all, there is an open source system developed at Meetup. There are two actually. One is called AX, adaptive experimentation, and the part of it is AE, or I'm sorry, adaptive. There's AX and PyTorch. So PyTorch is Bayesian optimization in PyTorch, and this is all available. People are working on this. There's great documentation. Just to repeat something I said during the talk, that the reason to use Bayesian optimization is that it's unrivaled in optimizing a function where you have a limited number of attempts. Basically, the way it works, it may start with a prior or it may start with no prior. You can throw a dart, try some hyperparameters, see what happens. You have 1 point. Now that's your prior. You could try 3 things at the same time. Now you have 3 or 4 points, and that adjusts your prior. And so with every new step, it tells you where to try, what configuration to try to get maximum information. And then it tells you where the minimum or the maximum of the function is likely to be. Okay. And so compared to other methods, it is shown to be very frugal. That's why we use it. You could use another optimization, but one thing is these functions are often not differentiable, sometimes even not continuous, and you don't even know a closed form, right? So there are other, there are packages even from Meta that are good in some cases, but they all tend to require more attempts. Yeah. Okay.
Any more questions?
Question, yes.
Yeah, thank you for all this. But you mentioned an example with a button. Can you give an example how the grid is working? So on which basis you can decide which color works better for you?
Yeah, so it's not hard to explain, but again, just I have to say as a disclaimer, I can't tell you exactly how the system actually works. I can tell you how it could work, right? And that will be pretty close. So for each user, there's a number of features right? For each, let's say you're doing this on Facebook, right? With the Facebook app. For each user, there's a number of features. How much time you spend logged in today? How much time do you typically spend logged in? Do you typically look at pages within the country or abroad? Do you typically, I don't know, go to the marketplace? Do you have a calendar on Facebook? Do you have events, right? Any of these things. And the number of these features is slightly over 100 for the purposes of this. And when people try to predict something, for this personalized experimentation system, there is a very simple simplification. They don't have to do feature selection because there is a standard set of features about users or about pages. They just take all of them. If there's enough data to use all of these features, they use them. If there's not enough data, then probably it's not a good thing to do, but they could try to use fewer features, not overfit. It's possible. Then they have to down select the features. Now, so what happens in practice typical of the system, not to mention specific features, they take the standard set of features, they train a model. If it looks promising, then we look at whether feature extraction is possible. We can run feature selection automatically to down select, and this is model-based feature selection. So there will be fewer features, right? Many of these features are useless for any particular prediction, right? So you could down select to 23 features, and that's your model. Then you run this model in the canary mode, see if it actually predicts something, or and then you put it into the product, and then you have sometimes holdouts to see if it actually works with product impact and all. Does that answer the question?
We have questions online.
Yes. Where do I chat? Yes. Okay. What was the most significant unsolved problem for end-to-end systems such as Looper? I can tell you that well, I could look at this as a machine learning question, as a systems. So on the systems side, mobile, making this work nicely with mobile was difficult. We tried it. We decided it's not worth it. So mobile is maintained by different by PyTorch mobile. On the ML side, unsolved. I would say we solved. So there's a problem that we solved in an intern project, but we haven't implemented this. So I gave you model types that we use, right? And basically, in the predictor, the real-time inference component, only certain model types are supported, right? If you suddenly want to do an ensemble of a couple of different DNNs that use each other's output as input, can't do it. Okay, so we have people working not in our team on supporting more different model types, but we came up with an idea how to take any model type. So you train a model of your favorite type, could be some Frankenstein model, produces great results, and then we train a GPT that mimics the behavior of this model. And that's a really great problem, which I think we solved, but we haven't really, we solved it as a research problem, but not as an implementation task. Okay. All right. Can I answer another question?
Okay, let's go with the last one question.
Okay.
Go ahead.
Oh,
So you mentioned product impact here. I was curious how you define that, and like what feedback metrics do you use, and like how do you track the effectiveness of the impact?
so at Meta, there is a system that maintains product metrics, and there are hundreds of them. And so for a particular product, they care maybe about user engagement. Maybe they care about how many people. So for example, for the password login prompt, I'm using it because we have a paper that describes the details. So there's nothing secret about this. But basically, how many users are successfully logging in is very important, right? And so that's a product metric. How much money was paid on SMS to help people log in is another product metric. You balance them. You want more people to log in, but you don't want to send SMS to everyone because that's expensive. Okay. And just a real quick question from there was, is this a low-code platform? Yes, only the APIs need to be written by product engineers. No ML code and a very limited amount of product code. Okay, I'll be around. If you have more questions, that's fine. And for those remote, find me on LinkedIn. I can answer some more questions.